The bone that is strong, because it is hollow, structural efficiency. A large animal bone may look like a heavy solid rod, but cut through it and the surprise appears, much of the inside is empty space, marrow, or a delicate lattice. The strongest material is concentrated near the outside. That seems risky. Why would a body build bones with hollow interiors instead of making them solid all the way through? The answer lies in how bones carry load. When a long bone bends, the outer regions experience the greatest tension and compression. The material near the center contributes less to resisting bending. Engineers know the same principle from pipes, bicycle frames, and bridge members. A hollow tube can be much lighter than a solid rod of the same diameter, yet still resist bending very well because most of its material sits far from the central axis. This gives bones a high strength-to-weight ratio. Weight matters. An animal has to move its skeleton with muscles, spend energy carrying it, and absorb forces when it runs or lands. If every bone were completely solid, the body would be heavier and movement would be less efficient. But bone is not simply hollow like an empty metal pipe. Long bones often have a dense outer shell called cortical bone. Inside there may be marrow and a network of spongy trabecular bone. These tiny struts are arranged along lines of stress. They help support loads from different directions while saving material. Bone is also living tissue. It can remodel itself over time, adding material where stress is high and removing it where it is less needed. Birds show an especially striking version of this design. Many bird bones are light and some connect with the respiratory system, but they are not fragile tubes. Internal struts and carefully shaped walls help preserve strength. Flight demands low weight, but it also demands bones strong enough to handle takeoff, landing, and wing motion. A common misconception is that hollow means weak. Hollow can be weak if the walls are too thin or poorly shaped, but a well-designed hollow structure can be stronger per unit weight than a solid one. Bamboo, many plant stems, aircraft parts, and bicycle frames all use this logic. The broader principle is structural efficiency. Nature and engineering both face the same problem: how to place material where it does the most work. Empty space is not always a defect. Sometimes it is the reason a structure can be both light and strong. A bone is not strong because it is packed with material everywhere. It is strong because its material is organized. The body saves weight by leaving space inside, and strength comes from where the walls are placed.